Yeah, thanks for the invitation to talk today. I'm Eric Trautmann. I'm a research scientist at Meta Reality Labs now and an adjunct professor of neurological surgery at UC Davis. But the work that I'm talking about today was work that I performed as a postdoc at Columbia. And I'm going to skip all the background here because you guys have been hearing about this for a couple days now, but specifically tell you about the NHP probe that Carolina just mentioned and how we're using it in how we're actually using it in non-human primates, and also how we're adapting this to using it with human participants during neurosurgery applications. All right, so my PhD and postdoc work was with rhesus macaque monkeys, and their brains are obviously considerably larger than mice. So we wanted to develop a probe that would access as much of the brain as possible. The original Neuropixels 1 is 10 millimeters long, of course, and this becomes really quite short even for accessing cortex when you have to contend with the skull and the dura. And while we were successful in trying these original mouse neuropixels in monkeys, it was extraordinarily challenging and really quite limited. We were only able to get, we were only able to get to, 3.5 millimeters into the cortex, and the shank was extremely flexible and difficult to traverse the dura. So working with IMEC, the team at IMEC did some incredible work to design a probe variant that uses essentially the same base electronics as the Neuropixels 1.0 probe, but with a longer and thicker shank. Somebody just asked a question about durability, and this essentially solved all of our challenges with durability. The shank is now came in a couple of thicknesses, but where it's 45 millimeters long, and went from about went from a little over 20 microns thick to around to a little over 90 microns thick, and the engineering involved in that was completely non-trivial, actually quite challenging, but it's essentially for users the same exact thing. We use it like we would a regular Neuropixels 1.0 probe. And for anyone who's curious, there's a preprint up now, and the actual publication will be coming out in hopefully just a couple of weeks. And so the raw signals we record from the probe are unsurprisingly gorgeous. They're essentially the same thing that we're used to looking at with the Neuropixels 1.0 probe. There's an example of 384 channels spanning the lamina of gyral motor cortex in a rhesus macaque monkey. And as we expect to see, we get individual spike templates that extend across many adjacent channels, and this provides us the ability to perform automated spike sorting using Kilosort or your other favorite algorithm, and also automated drift correction, which turns out to be completely essential for primate applications. We are able to achieve quite stable recordings, but oftentimes if a monkey's moving during a behavioral experiment, we could see more drift than you might expect with a mouse. And for primate systems neuroscience, this has been completely transformative. Here's an example in the visual system where it has been tedious or impossible to systematically map all the visual areas. So experiments were disproportionately focused historically on recording from V1. But in this experiment from Ruobing Jia and Shudi Zhu in Tieran Moore's lab at Stanford, they recorded from 3,029 neurons in a single session. And we're able to do this by inserting the probe to a final target location, and then sequentially recording from all of the banks that were inserted into the brain. So 384 channels at a time while performing the visual experiment, and then selecting from bank 0, bank 1, bank 2, all the way up through bank 4. And that already is a pretty transformative capability. I don't think we've never been able to record anywhere near that many neurons in a single session before. Previous technologies are capping out around 32 channels, so this is completely transformative. And this is what that actually looks like. You can see the individual spike templates of all of the neurons and their receptive fields. So for mapping purposes, this is a big deal. Now, we're also able to record from multiple probes simultaneously. So working with two colleagues, Andrew Zimnick and Saurabh Vyas in Mark Churchland's lab, we designed a system for simultaneously recording from the basal ganglia, the supplemental motor cortex, and the primary motor cortex. And this is during a sequential reaching task. And I'm just showing you the trial average firing rates for 12 example neurons, 4 from each area. But we recorded similarly 384 channels in each of the target regions during this task. And this is the first time we're able to actually record large populations in deep brain areas, which opens up a lot of exciting experimental opportunities for topics like motor learning. Previously, before we had Neuropixels, we were limited to using Utah arrays to record from superficial areas, or technologies like V probes, where we could record from a dozen neurons in deeper areas, but really nothing like this before. So the primary challenge for using Neuropixels in primates is to precisely target and stably hold the probes during a behavioral experiment. Otherwise, they're relatively turnkey, as you guys already know. So we've developed a number of methods for inserting and targeting, and all guided by this design philosophy of attempting to minimize the skill that's required by an experimenter while performing an experiment. So our idea is, like, if we can make it as safe and easy and straightforward to use as possible, then this reduces the setup time and allows us to put more probes in also. And it's just easier for everybody else to use. So here's a system that, like a newer system, where we're using MRI to image the brain ahead of time, design a recording chamber that fits the skull, use it to build a CAD model of everything ahead of time, and design our, I don't know if you're able to see this video. It seemed like there was a little bit of video lag. But
Yeah, we can see it.
okay, great. So we really have everything in a CAD model. We can work out the 3D geometry of our recording targets, and also design, using 3D models of the Neuropixels probes, make a really complex insertion geometry that minimizes the interference between the probes. So we worked that all out ahead of time. Before we'd come up with this approach, it was really much more of a process of trying to work it out during the middle of experiment, kind of fit in multiple probes at once. And that's just non-viable when you're talking about the level of complexity that we ended up finding ourselves dealing with here. So this allows us to pack in a lot of probes, verify that it'll work ahead of time, and hit targets precisely without mechanical interference and without making any judgment during an experiment. And that's made it possible to perform a number of otherwise very challenging experiments. Here's a picture of this approach used in a second monkey. So this is, so all of this hardware is just on top of the monkey's head. In this case, we have 8 probes simultaneously inserted, all into a 3mm patch in motor cortex, so they're converging on a small area. And while this gives us the unprecedented ability to record neural activity at scale, it's still kind of a bit of a pain because because it's acute recording. We have to insert and remove the probes during each session. So some of it, what we're looking at now is how do we work on semi-chronic implantation. So if we could implant the probes semi-chronically for up to a few weeks, that would enable a bunch of experiments that aren't really possible currently. All right, so in the last minute or two, I want to tell you about some other work that we're doing with collaborators who have been pushing on trying to use Neuropixels in human patients. In 2022, there were 2 papers that came out, one from a group at MGH and one from a group at UCSF. So Angelique Paulk led this first effort, and Jason Chung led the second. And both of these essentially were quite similar applications of using the original mouse Neuropixels in human patients during a neurosurgery to, typically epilepsy surgeries to resect tissue, and you can record from that tissue, record from awake patients before the tissue is resected. This next slide shows surface of a human brain, which some people find queasy. So feel free to look away for a second if you prefer not to see an intraoperative photo. But this is what a neuropixel recording during a neurosurgery looks like. It's kind of about what you would expect. Essentially the same hardware, the same 1/4-inch dovetail mount rod that you guys are probably familiar with now. But with some additional challenges due to the fact that the brain isn't stabilized and that everything has to be sterilized ahead of time. And then your entire experiment needs to fit into about a 15-minute window in the middle of a surgery. So the primary challenge with this type of experimental workflow is that you get a lot of motion. So here's a drift map, and quantifying the motion over time, you see that there's a lot of pulsation, which is due to respiration and the pulse. So that causes the tissue to bounce around on the probe, and we're a lot more limited in what we could do to stabilize the surface of the brain during a neurosurgery. Despite this challenge, spike sorting can still be made to work pretty well. We don't get the same kind of yield as if you were able to perform really stable recordings in mice or primates. But there's some really nice science that's started coming out from these efforts to map phoneme structure in temporal cortex. There's a nice paper from Eddie Chang's group last year, and I can point you to some of those other papers. So I think I'm about at time here, so I just want to very briefly mention that we're also looking at moving into the semi-chronic applications for the epilepsy monitoring unit with human patients. These are SEEG probes, and we eventually want to replace those SEEG probes with a Neuropixel-like device that you could leave in place for several weeks. All right, so with that, I don't know if I have time for a couple of questions, but I will leave it at that. Thank all of my numerous collaborators. I'm really representing the work of dozens of people here across a number of labs. And of course, the team at IMEC, Carolina and Marlene and Tim Harris and Barun Dutta, who have done spectacular work helping us get here. So thank you, everybody.